Okay, thank you very much for having me here for this this workshop. It's quite a nice workshop to come to and be invited to. I've sort of touched on benders a lot of times throughout, I guess, since my PhD. It's sort of one of these algorithms that I just keeps coming back to. When I did my PhD, I always used to think that Bender's decomposition was one of the worst algorithms to implement, because whatever you do it the first time, and then it never really works. So you have to do all this other stuff to make it sure it actually works. And we saw that in a lot of these other talks that we saw today. And so that kind of led me to some of my work that took me to implementing a generic Bender's decomposition framework. But my question now is, from that implementation side of things, like, given that we have this software, we've got, like, I'll go through different software packages we have available, should we actually be implementing Bender's decomposition from scratch anymore? Like, is there really a reason to do that? Or if there is, like, or should there, like, I guess the other question is, should we not be implementing it? Like, should we actually, if we have to implement it now, should we actually be thinking about developing software so we don't have to implement the base algorithm anymore? Okay, so just to start off with, so just generic setup here. I know we've spoken about, like, we've seen what's going on in this this workshop before, but I want to just set the scene of looking at what I call structured mixed integer programs. And I care about the particular structure, though, so the structure that we need for Bender's decomposition. So we have our first stage variables, the x variables, and our second stage variables, the y variables, and then we have this. So the x is then like your linking variables, and then you have the y variables, which are then like in your second stage you can solve for once you know the realization of the x. Okay, so in this case, I've taken quite a general view. So I assume that x could be integer or continuous, and then the same for the y's. So I don't want to restrict this talk to just classical Bender's decomposition, because we have strategies, and as we've seen, the strategies to handle different cases. And so I want to sort of make it more general to be able to, I guess, handle all cases that Bender's decomposition can be applied to. And we know that it's not necessarily easy when you've got certain setups, but I'll go into some bit more detail in just a moment. Okay, so from this, I guess this basic setup here for a structured mixed integer program, we all know how to get to the Bender's decomposition component. We have now the master problem at the top there, so we've taken all the y's out. We'll be able to write this completely in x. And then we have our sub-problem, which is given there, which is completely in y, and then we have a fixed x. Okay, so then we have, if we just had if our sub-problem was just continuous, then we care about or if you just only look at the continuous relaxation, we care about the extreme points of also our set O, which is the extreme points of the dual of f, and then we've got our set F, which is all the extreme rays. And so they correspond to our optimality and feasibility cuts, respectively. And then if we care about the discrete problem, then we would have some integer cuts. And so we saw those in previous talks. We have some cuts that look a bit like no good cuts. And then we also have, so we could consider this as a logic-based Bender's setup as well. And so you'd be, again, no good cuts or some other cuts to be able to remove the, I guess, the infeasibility you find from when you solve that sub-problem. Okay, so that's our main setup. So then I'm going across things that we actually have talked about earlier today. So we have now, I guess, two different algorithmic approaches for Bender's decomposition. And you actually see both of them come up quite regularly. One is something conceptually a little bit easier than the other. And so, like, I guess this is the more conceptually easier approach, because this is, I guess, what we first viewed Bender's decomposition as. And when I was doing my PhD, I guess I came across a blog by Paul Rubin, where he wrote about Bender's decomposition now and then. And this was the then at that point, which is probably about now, I guess, 15 years ago, but then that was still an older blog. And so this is, I guess, the traditional setup. So we know it, we solve the master problem, and then given the solution to the master problem, we then solve our sub-problems, and then we have some kind of optimality check. Yeah. And so we kind of go to this. This could be like your textbook approach. It's easy to understand. You can implement it fairly easily. It doesn't take too much effort. Unless you're using something like SCIP, it becomes a little bit more tricky. But generally, it sort of comes together fairly well. Like so, if your solver of choice is Gurobi or CPLEX or something like that, it's not too hard to actually work with. But then we have this. There's some implementation and computational issues associated with this master problem. If it's very difficult to solve, then you end up with this case where you're solving a very difficult problem multiple times. And then so you could actually get this very large overhead by repeatedly solving this master problem. There are strategies that can be used there. So we do know you can collect solutions. So most solvers do store all the solutions that are found during the search process. So you can collect solutions, generate multiple cuts. And so there are strategies that can work with this particular implementation. Now, so that's so I'm not going to say one's better than the other, because we do know that with any particular optimization algorithm, this could actually be very good for a particular problem type. So yeah, I'm not going to say one's better than the other. We've got different names for this. So I call this the branch and cut approach. So it's like it depends on how you, I guess, frame it in your mind. For SCIP, I guess it's like this sort of setup here. This solving process setup is the solving process from within SCIP. I can't really tell you what happens in other solvers, but this is kind of what you would see. What's going to happen when you actually hit play on a I guess mixed integer programming solver. So you can see there's lots of different stages that you go through. You've got this node processing, which then we sort of blow up here. Lots of stuff's happening inside that node processing step. And so, like, I guess with modern MIP solvers, and from that Paul Rubin blog, we have this, like the now approach was the fact that we have callbacks, essentially, in modern solvers. And so from these callbacks, you can then interact with the optimization a bit more, so you don't actually have to wait till the end in order to be able to generate your Bender's cuts. So for SCIP, and like, I guess if you're using these lazy constraint callbacks, this is kind of where the sub-problems would be solved. So you have within your node processing, you get to the end, you check integrality, and so then if you have an integer LP solution, then you'll then send that to your sub-problems. Okay. And then on the other side, you've got, with your primal heuristics, you need to also check whether your primal heuristics are actually proper primal solutions. And so we actually can be more integrated with the solving process. And so that's I guess, why people think this is more modern, more advanced, because you're actually working with the solver as opposed to sort of treating the solver as a black box. There is this extra step here, I put in dotted lines, whether or not you want to use that or not. So this would be essentially the McDaniel and Devine two-phase method. So if you, in the root node, if you were to solve your Bender's subproblems at that point, then you're generating Bender's cuts from LP solutions. And so then that would, so that's just another step that you could use. You can also do it throughout the tree. I've tested it out a few times. It never really works very well, but you can generate cuts from LP solutions during the tree search. And I guess that's something I've always been curious about as to whether you could generate more LP cuts during the tree search, but I've never been able to find a good strategy at this point. Okay, so they're the two setups. Now, when we're talking about implementation, so you could easily implement Bender's in one of these two ways. So for, like, as I said, for solvers, so where we've got these the solving Bender subproblem steps, that's just a lazy constraint callback. In SCIP, it's called a constraint handler. There's a little bit more involved with the constraint handler, but it's still the same concept. Okay, so what implementations are available for Bender's decomposition? And so this is not an exhaustive list. So there's plenty out there. There's people actually, I know of people who have very advanced own personal implementations of Bender's decomposition, which could easily fit into these lists if they happen to make them public. But so this is I guess, some implementations that are available. And so, technical issues again. So I can keep going on that. Everyone saw the names anyway. So CPLEX, I was a bit disappointed with CPLEX. They beat me just before, so they got their implementation out before I got SCIP out. But then so they have a classical Bender's decomposition implementation. And so that's then just a, so they would have so they only consider the case where you have the, I guess, continuous subproblem. SAS just recently, I think in their last version, they've released a Bender's decomposition framework. They used to have for Danzig-Wolf reformulation, they had a framework for that, and now it's just so they've also extended that now for Bender's decomposition. And so in those cases, what they have is so they've got both for CPLEX and SAS, they will so you don't really have much interaction. You just put in your problem, and then you'll get your solution back after solving it with Bender's. They do have some enhancement techniques that you would typically expect. CPLEX actually has a very nice talk that they gave at CPAOR a few years ago, where it was talking about all the things you have to do in Bender's decomposition to actually make Bender's work. So that was quite nice. And so SAS has done a similar thing. So they've sort of taken similar approaches there. Coluna, this is a package that's actually more designed for column generation. So it's a column generation, but then they've sort of looked at structured problems more generally. And so this is a Julia package built on top of Jump. And so there again, it's classical Bender's, but they've got some flexibility in their setup. So that's something that I think there's potential on how what you could do with that. But at the moment, it's only it's work in progress for them. So they've just got classical Bender's decomposition at this stage. Nutmeg, so that was mentioned earlier in John Hooker's talk. So that's a logic-based Bender's implementation. So that's built on top of SCIP, not using the SCIP Bender's decomposition framework. They sort of implemented it themselves. And so they're actually using a separate CP solver for the subproblem. But again, it's out of the box. You can solve things using Bender's decomposition without doing any work. DSP is a dual decomposition solver with classical Bender's decomposition available in there. So where this came about is that they use dual decomposition and then they solve. So they actually use Bender's cuts to strengthen that algorithm. And so then they thought, well, we've already got these Bender cuts being generated, so why don't we just use classical Bender's as well? And so that's so they're the main ones. And so I've made SCIP separate, not just because I wrote it, but more that I wanted to. There's a slight difference between the ones up above here. So the ones, so the previous ones are pretty much just they treat it as black box, so you can't really do much with them. So you just put in your problem and then you get an answer using Bender's. With SCIP, there's a little bit more flexibility you have available in there. I'll talk about that a bit more, but essentially there is, the other difference here is that there are some extra cases that can be handled by SCIP. So those, I think we heard from an earlier talk where we got, if you have integer variables in the subproblem, then you are restricted to a particular master problem setup, which is purely integer, mainly. Purely binary. So then, so those cases are actually being handled within SCIP, but the other ones don't handle that. Nutmeg would handle it, but it's treated as a logic-based Bender's approach. So they don't do any classical Bender's cuts. Okay, so that's like a setup. So there are these implementations available. So then, I guess that's where my question comes from. So we've got all these implementations. People have made these public. So why should we use them? So why aren't we using these? Why are we implementing Bender's ourselves? So the typical features that we have, you can just have your file, put it into these solvers, and there's the certain formats that you need to use. You don't actually have to, the user doesn't have to worry about it. So for industry, it's actually quite good. So if you say, okay, I want to use Bender's decomposition, let's go. We can just test it out using CPLEX. Now, they're typically implemented using the branch and cut approach. So you don't have any flexibility in that. That's it. So if your problem happened to benefit from using the standard implementation, then you wouldn't actually get a chance to use it. You'd have to implement it yourself at that stage. There are some enhancement techniques available internally. Whether you can turn them on or off, that's another question. I know for CPLEX, you can't actually change much. And then there are some structure detection aspects. So CPLEX and SAS, they take the continuous variables, put it to the subproblem, and then keep the integer variables to the master problem. But you're not getting too much, structure detection there. The difference would be SCIP, which uses GCG, and there's some automatic structure detection that is being used. So you can even if you don't know the structure in your problem, you can actually run with GCG and still use Bender's decomposition. Now the limitations of this though are you can't really do much with it. So if you want to use Bender's, you're stuck with what the developers thought they needed for that to run a Bender's decomposition algorithm. And we've seen from the previous talks, you're not doing standard Bender's most of the time. You've got something else that needs to go into it to make it work. So whether that's the adaptive cuts, so you don't want to do like multi-cut or single cut, you want to do something in between, then you can't do that. You're stuck. You've got to do one or the other. Now, well, actually in this case, it's actually more multi-cut approaches anyway. So if you want to do something other than multi-cut approach, you can't do it. You can't change the cut generation methods, or the sub-problem solving methods, or even the master problem solving methods. So I remember talking to some people and they said, oh, well, we'd really love to use CPLEX, but I've got this great sub-problem solver and I can't use it because they need to solve the sub-problem by CPLEX. And so there's no real flexibility in that case. So we're kind of a bit stuck on so if you want to do anything more, I guess, exotic with your Bender's decomposition, then there's not really much you can do. You've got to implement it yourself. So SCIP's a little bit different in that case. Now, I'm not going to say SCIP solves all these problems. It definitely doesn't. But you can actually, you can implement different components. Now, a bit of a caveat here. I know how to do all this because I wrote the thing, and I also use SCIP. So I can do all that. But that's a massive limitation here. People don't necessarily know how to implement these aspects because SCIP's a beast. And it takes, I think you almost need a PhD to learn how to use SCIP in the first place. You can actually change your master problem solving methods. There's this thing in SCIP called a relaxator, and I don't know how many people have ever really used one, but you can use it, and that would get around this aspect of you having a different master problem solving method. Within this Bender's decomposition framework, so it's really just a constraint handler and then some fancy stuff that happens around it. So you can actually change the solving methods. Then you actually have to implement quite a lot of stuff. If you're just using the default implementation, then there's not a lot that has to be done. There are different cut generation methods, so optimality, feasibility, integer cuts, no good cuts. You can put in your own cut generation method. Now that's a bit easier than doing your own solving methods. And you can combine the two if you want to, but if you start doing that, then you really are doing a lot of implementation work. But there is flexibility here. That the question is that flexibility enough? Can you do what you want to do with it? I'd say it could be. So that flexibility could be enough for you to get a long way down the track. Depends on what you want though. So there's some things that you couldn't do. So I do know for sure that the adaptive cuts you couldn't do without a lot of work. So then also how well you know SCIP. And then whether SCIP is enough, okay? So you may be coming from a background where you use Gurobi all the time. So then if you use Gurobi, then SCIP's probably not going to be enough even with Bender's decomposition, it may not be enough to beat Gurobi. Particular problems, that might be true, but that's a question of whether it's going to be enough for you or not. Okay, so yeah, I think that's a big caveat though. You need to know SCIP because I am curious, how many people in the room have actually used SCIP? And then keep your hand up if you think SCIP is easy to use. so that's that's kind of answers my question here. Okay, so some examples on what you could do. So this is this example actually, I didn't know you could do this, but I ended up having to do it, and it worked relatively well. So I needed to make sort of the classical approach work, and because I had an alternative algorithm that could solve the master problem, and it could solve it relatively well, so I could solve the MIP quite quickly, but I didn't want to do the branch and cut approach. And so I had this thing called a relaxator. So it just converts the SCIP problem into this alternative algorithm, and then once I solve it, I just send the solution as a primal solution, which then generates cuts, and then that will put the cut into the master problem, and then you repeat. So this is It's a bit of a hack because it wasn't actually a primal feasible solution. It was just a solution to the master problem. And then like in the SCIP world, it didn't really work, but it did the job. So you could do that alternative master problem solution method. And this was another one where this did take quite a bit of work. So graph golf, which I don't expect people to know what that means, but essentially there was we had this Bender's decomposition algorithm where the sub-problem was the shortest path algorithm. And so the shortest path algorithm we didn't want to solve as a MIP because that seems ridiculous. So we wanted to solve that using like the appropriate algorithms. Shortest path problem. So then I implemented my own Bender's decomposition plugin to then have that algorithm being run. And then at the same time, I need to implement my own cut generation methods. So like the implementation effort is starting to grow. But we were using the core, so we didn't have to worry about like handling of cuts, the handling of like when the subproblem should be solved or not. So at least we didn't have to worry about that part, but there's still like, you're not too far off implementing it yourself at this stage. Okay, so there's some things you could do, but there are limitations. So now this, I took this figure from Rahmani so this is the literature review on Bender's decomposition. And so I wanted to sort of show where the implementations currently sit, okay? So I'm going to abuse this cut generation one a little bit. So what the letters mean, so the CC means classical and I means, or C means classical and I means improved, and the first one's feasibility, the second one's optimality cuts. And then the S's for solving methods, so it's standard for master and sub-problem, and then A is advanced solving methods. But on this cut generation one, I'm going to say, well, does the solver let you do any improvements on it, okay? So typically the generic implementations that we have available, so your CPLEX, your SAS, like Kaluna, the DSP, they sort of sit here. And so this is what they said in the paper is the landscape of what you can do with Bender's decomposition. So we're not getting very far, are we, with these generic implementations? So then with SCIP, so it does actually extend out a little bit more. You can do a bit more stuff with it. There are limitations, of course, in terms of how much effort you want to put in. And then if you do with the custom master problem, it does actually extend out a little bit more, but that's like you're sort of really hacking with SCIP at that point. So I wouldn't actually say that's a standard one. So we'll say that where SCIP is about here. But even at that point, we're still a long way from handling everything that people like care about or what we say can be done. So like I'm already starting to get to the point of that, like the answer to my question, do we actually need to implement it? And the answer at this stage is probably we do, because we not, like there's things that we want to do with Bender's that we can't handle from these generic implementations. Okay, so here's just some examples of what's missing. Okay, so like I mentioned this earlier, we have like nearly all of the implementations use a multi-cut approach. If you want to do something in between, no chance. You can't do anything with the sub-problem. It's sort of, you have to solve it as a MIP or LP. You can't really do any approximate solving. And then, like if you want to generate cuts from other solutions outside of just what's coming from the tree, or like generate from multiple solutions at a time, then like you can't, that's not possible. Parallelization, you're stuck with what they decide was the best parallelization techniques. If you have some stabilization techniques that you might have with the cut generation, they're very difficult to implement within these generic frameworks if you can do it at all. The master formulation is just set. You have to do whatever you start with, so you can't change much. And there's plenty more here. If you go through that literature review paper, you'll quickly see that there's a lot that can be done that can't possibly be handled by our generic implementations. Okay, so there's my question. Should you implement Bender's decomposition? So I'm going to actually say here that initially, no, you shouldn't implement it because we do have generic implementations. But you probably will end up at some point implementing Bender's decomposition. And that's because what you should do, what I would recommend to anyone who thinks that their problem is suitable for Bender's decomposition, is to just use one of these solvers. Like we've got these solvers available. From an academic context, you could use CPLEX or SAS quite easily, and And in that case, you just, like the interface for CPLEX is pretty straightforward. You just need to put in your MPS, some annotations, and press play, and like hopefully it does the job. And if it does the job, then you're done. Unfortunately, your PhD might need a little bit more work to go with it, but like you don't have to stuff about with implementation and spending a year of your time implementing this thing. And then again, if it's useless, like you probably, like, are you really going to gain a lot from implementing it completely yourself and then doing some fancy techniques? Like if it is useless, then maybe you should be thinking of other algorithms. But if it's promising, then actually, yeah, maybe you should think about doing a bit more. So it's a great testing tool. So you could really work out whether Bender's decomposition should be implemented or not, really from this straight up. The next I would say to use, so if it is promising, I would then, so in my case, I'd use SCIP to implement something special, because that, like the effort there isn't so great, or you'd use some lazy constraint callback. They're a bit more effort if you're implementing your own lazy constraint callback. Again, you've got the same questions. If you've done a good job, then great, finish, go home. If it's useless, then stop. But then if it's promising, you might want to continue a bit more. And then finally implement it all yourself. Yeah. I'd say at this stage, SCIP's probably not the best choice. I'd go with something else. But if you love SCIP, and there wasn't enough hands to say they love SCIP, then I'd probably go with another approach. But yeah, if you do get to that more promising step, especially if you started going down the lazy constraint callback method, then you've actually halfway down into step 3. So then adding these extra parts actually works quite well. For non-classical problems, then you're kind of a bit stuck. You have to implement it yourself, really. So SCIP does handle some cases. So nonlinear programming is possible in SCIP. But we do, like in that case, we do treat it as like a logic-based Bender's approach. So we solve the MINLP in the sub-problem as like directly, and then we generate no good cuts. So it's not an ideal setup, but it can be handled. That's kind of what we wanted to do there. So in this case, if you've got a logic-based Bender's approach, I'd probably, you could use Nutmeg, but I'd probably be looking at something, implementing it yourself. Now, what would be my thoughts on whether, what would be a good implementation for this particular, for having a framework? And I think this is, I wanted to think about this a bit more for this talk, because, we are missing something. And so, we should be able to take the core algorithm of Bender's decomposition, because it's not a very complex algorithm, and be able to have a framework where we can actually add on the bits that we need, or make it, that can be flexible enough for us to be able to implement this, without having to implement the core of the algorithm, because we should be able to just tack on the bits that we want. And I think that my aim with the SCIP implementation was to make it so it was flexible. SCIP has this nice plugin structure, so if you understand what's working, how that works, it's actually very nice to extend. And so that was the idea behind the Bender's framework. So I built it in the same way with this nice plugin structure. So you could, say nice. I'll say plugin structure. Nice can be someone else's opinion. So the idea was that you can extend it and build on it to be able to do what you want to do with it. But the problem is you're kind of stuck with SCIP, and that doesn't always. It's not the fastest solver, is it? There are better solvers that you could use, and I think that if you're going to have a framework for Bender's decomposition, you want to be able to, use different solvers. I think Kaluna has gone down the right path here for structured mixed integer programs. They're built in Julia, built on top of Jump, so then you can use different solvers if you want to. The data structures that are being passed around, especially in the SCIP setup, there's just too much. To be able to understand what's going on, you just you need to know a lot more about SCIP than you probably should in order to be able to actually use it. And so I think that you would want to really slim that down, the information passing, because if this is going to be used by all users, and if you're thinking PhD students who are coming in that want to use Bender's decomposition, they probably haven't had much experience with solvers, let alone tweaking one. And so you don't want them to have to be stuffing about with too much, too much core code, okay? So you want to be able to slim down the information that needs to be passed around to really the core stuff. part of the main issues that I see with these implementations is that the master and sub problems, you're really stuck into this branch and cut approach, so you have no real change to that. So you'll have, like, they've got their roles in the solver, and so you have to then follow exactly those roles. So if you could split these roles up and actually get them to be called a little bit more independently throughout the algorithm as to how that works, that's very much a design issue. And but being able to be call these sub problems and even the master problem in many different ways throughout the algorithm would help us actually being able to do more of these, like, I guess, more advanced algorithms, because, like, there are lots of cases where you want to solve the master problem in multiple different ways in order to be able to get different cuts or, like, do perturbations on it. The sub problem's the same thing. If you want to be able to generate more cuts from like from doing generate more cuts from different solutions, you don't necessarily have that opportunity in the current setup. Termination criteria is always being controlled by the solver. There should be more control over that. And also the core features should be more available. And I'm talking from a SCIP perspective there, where they're not really available to people. The setup that I showed you before, I don't think anyone really knows that exists. So yeah, I think that there's not the understanding of what can actually be done with these solvers. So to summarize, so we have a lot of generic, there are a number of generic Bendis decomposition algorithms, but unfortunately there's not really one that suits for all purposes that we want. And that's probably never going to be the case. But we do see, say, for example, with MIP solvers, we do have MIP solvers that do suit most cases for solving MIPs. So there should be, why can't we actually have such a thing for Bendis decomposition? Given it is such a, I guess, well-used algorithm, why can't we implement such a thing? So we can actually use the current implementations as a testing tool, and I think that's a great use of this. And I think it should be possible to develop a generic Bendis decomposition implementation. We haven't done it yet, but I don't think it's impossible. I think there is something that can be done there. So my questions are: should you implement Bendis decomposition? I think the answer is still yes. I think there is still very much a use case for that. But should we need to? I don't think we should need to implement it, because I think we should be able to develop something, or even more than just one solver, multiple solvers, that give you the core algorithm that we don't need to implement that, because the core algorithm isn't really where the fun is. It's the things around it that we want to be implementing, and I think we should be able to get around that with some new and better generic implementations. Okay, thank you very much.